Alright, so we're going to do another problem. That's problem 61. A 30 kilograms wheel, initially essentially a thin hoop with radius that's 1.2 meters, is rotating at 280 revolutions per minute, so it's the angular velocity. It must be brought to a stop in 15 seconds, which means that the angular velocity, the final angular velocity should be 0. How much work must be done to stop it? And so you want to find the amount of work to stop it, and what is the average power? Okay, so this is a thin wheel, and it's rotating. So with this initial, and this is the final, and you ask to find how much work has to be supplied in order to stop it rotating. So we need to first of all understanding that the net work done by the force has to be equal to the change in kinetic energy, right? You have the angular velocity, so you can calculate the kinetic energy, provided that you know what is the rotational inertia. So this is the amount of work that's needed in order to change the kinetic energy. So you have a kF minus ki. Now your kF, because the final angular velocity is 0, so there's no kF. Now initial kinetic energy, that will be 1/2 the rotational inertia of this thin wheel, and then times omega, initial velocity squared. So this is already given, but it's not in SI units, so we need to change that. So 280 revolution per minute, that will be 280, and then 1 revolution is equal to 2 pi, and pi is 3.14. So you multiply that and then divide it by, so that becomes radians, and minute, that's 60 seconds. So after you do the conversion, your omega I is equal to 29.32 radians per second. Okay, so you have that value. What about your I value, rotational inertia? Rotational inertia for this thin hoop, the rotational inertia can be calculated using this equation. That's just mr squared. So your m is 32, and your r is 1.2 squared. So your I value is 46 times 0.08 kilograms times meter squared. So you have this, that's negative 1/2, and your I is 46.08, and then times the omega, which is 29.32 squared. So you should get a value that's negative 1.89 times 10 to the 4th joules. It is negative because the amount of work done is to slow it down to bring it to a complete stop. So energy has to be taken away from the system in order for it to stop the moving. Okay, so this is the amount of work that needs to be done in order to stop this thing from rotating. And you're asked to find what is the average power. So to calculate average power, you have the amount of work that's done. You have the time interval information. So all you need to do is just use that information. So you have 1.98, and basically for power we don't have to include the negative sign. So you have 1.98 times 10 to the 4th, and then over the time, which is 15. So you get your power is 1,320 watts. Okay, so this is in watts. So that's joules per second, and this is the power that is required in order to bring it to a complete stop. Okay. All right. So the final problem that we want to do is problem 66. Let me just. Alright, so problem 66 has a very cool diagram. So let's draw the diagram. This, then it's a wrap, go here, then on top, wrapping, stand, then here, then here. All right, so let's look at this problem. Now this problem says that a uniform spherical shell of mass that's 4.5 kilograms, and the radius that's 8.5 centimeters, can rotate about the vertical axis on frictionless bearings. A massless core passes around the equator of the shell and over the pulley of rotation inertia that is 3 times 10 to the negative 3 kilograms times meter squared, and the radius is 5 centimeters, and it's attached to a small object, and this object has mass of 0.6 kilograms. There is no friction on the pulley's axle, and the core does not slip on the pulley. Okay, and what is the speed of the object when this has fallen 82 centimeters after being released from rest? So that's it. This is initial height, and then this is final height, and it's below the initial point. So that's negative 0.82 meters. Okay, so what is the speed when it has fallen? So what is the speed when it reached that point? This is initially it is at 0. Okay. And go from here to there, it has fallen 0.82 meters. And what is the velocity? And the whole thing, when it's moving down, this is rotating, and this is also rotating as well. When it's rotating, what does that mean? When it's rotating, it means that there is kinetic energy associated with the rotation, right? So this one will have a rotation energy. And this one also will have a rotation energy. And this one is moving downward as well, and so it has a kinetic energy. So all this energy are supplied by what? By the changing height. So because the problem says that use energy consideration. So this is basically the approach we're going to use. Okay. So what does that mean? It means that if we look at the whole this as a system, we want to see what is the kinetic energy and the potential energy initially, and what is the final energy. So in other words, EI is equal to EF. And your EI, the mechanical energy, involves kinetic energy and potential energy, and so forth, KF plus UF. Okay? Kinetic energy, initially, is not moving, 0. Regardless whether it's rotation or linear motion, there's no kinetic energy. And the potential energy, you can define it to be, define this to be 0 as well. So that this will be negative mgh. Right, because your h is negative. Okay, so negative mgh. So you have 0, 0 during the starting point, and then after it has fallen 0.82 meters, there is a kinetic energy. So which is 1/2, and then I omega square. That's a big one. So that's the shell, the sphere, and then plus sphere. Okay, and then plus 1/2 that's called that disk. So 1/2 d and then wd squared. This is the rotation energy associated with the sphere. This is the rotation energy associated with the disk, and then plus the kinetic energy. The kinetic energy associated with the block, which is 1/2 mv squared, and you'll also find v, and then plus the gravitational potential energy when it has fallen from this point to that point. This is your mgh. So minus mgh. Okay. We have the mass, we have the g, we have the h. So let's move it to the other side. So you have your mgh. That's equal to 1/2 the rotation inertia of the sphere, rotation this, and then plus this, and then plus this. So we need to figure out how do we plug in those numbers. So the I here, this is your ID. ID is given, and what about this? The I here, we're not given this one. So what is our I here? So our I here is equal to for this I, for this sphere, it is is 2/3. It is 2/3 mr squared. Okay, so we can, so you have the m, which is 0.6, g is 9.8, h is 0.82. We use we use a positive value because your negative is right here, so you move it over here. That's positive. It's 1/2. It's equal to 1/2, and your is 2/3 and then mass is 4.5, and your radius is 0.085, and then you square it. This thing square it. That's your 2/3 mr squared. Okay, and then omega. So what is your omega? Your omega, let's see. So your omega here, because the whole thing is moving, if this is moving at a velocity v, your omega, again, we're going to, your omega r is equal to v over capital R. And your omega d is equal to v over the radius, little r. Okay? That's how you associate the linear motion to the rotation. So this is 1/2 is omega s, your omega s is equal to v over r. So velocity over the radius, that's 0.085. So you square it. And then plus, I'm going to plus here, and then plus 1/2 your ID is given. This is your I, and then your omega. Your omega d is v squared, v over your r. Little r is 0.05. So this thing squared. And then plus 1/2 the mass of the object, which is 0.6, and then times v squared. So you can see that this is a number, and then multiply by whatever number, and then you have v squared here, you have v squared there, you have v squared there, so you can calculate your v. So after you plug in all this number, you should get your v value. That's equal to 1.417 meter per second. Okay, so you can see that this problem, although the diagram looks a little bit complicated, but when you use the energy conservation, then you know that the total energy in the beginning has to be equal to the total energy, after it has fallen 82 centimeters. And so this is our starting equation, and then we just need to think about what are the expression for the kinetic energy. For this one, when it's moving, it has the rotational kinetic energy. This also has a rotational energy, and this one has the linear kinetic energy. And then the gravitational energy is mgh. If we define this to be 0, then this has to be negative mgh. You can vice versa. You can define this potential energy at this point to be 0, then this has to be positive mgh because it's above the reference line. Okay, so that's that.